There are two key features of carboxylic acid derivatives. One is that they can be synthesized from carboxylic acids. The second is that all carboxylic acid derivatives can be hydrolyzed back to a carboxylic acid derivative. So first we're going to look at the hydrolysis of acid chlorides. Since acid chlorides are the most reactive of the carboxylic acid derivatives, they actually can be hydrolyzed in just water. So if you leave a container of an acid chloride open on a muggy day, like today happens to be, you're going to end up with a carboxylic acid. You can also do this in base, though having basic conditions is not super necessary with an acid chloride. One of the key things about reacting in base is that you'll end up with the carboxylate instead of the carboxylic acid. So if that's the species that you actually need, reacting in base will get you there faster without having to do an extra step. Acid anhydrides are a little less reactive than acid chlorides, but they're still on the more reactive side of our carboxylic acid derivatives. So they can also be hydrolyzed in just plain water. Now you have to be careful with the carboxylic acid derivatives, or the acid anhydrides specifically, because you're going to end up with two halves of the molecule. And if the molecule is asymmetric, that's going to give you two completely different products. So we would end up with one carboxylic acid from the left-hand side, and then you end up with a carboxylic acid from the right-hand side. So two molecules, both carboxylic acids. And if we do the reaction in base, we end up with the same thing. It's just that we end up with two carboxylates. So one from the left-hand side and one from the right-hand side. Our next species up are the esters. Esters are less reactive than acid anhydrides by quite a bit. So we're not going to be able to hydrolyze them in just plain water. We're going to need something a little stronger to catalyze the reaction. In this case, we need aqueous acid, and depending on the situation, sometimes heat may be necessary, but this hydrolysis can occur even without heat. And we will end up with carboxylic acid plus an equivalent of the alcohol that would be used to make the ester. And if we do this in base, we would end up with the carboxylate and the alcohol. Now this process is called saponification because this is the process through which soap is actually made from fatty acids. Our next species are the amides. Now, amides are actually much less reactive than esters. So in order to hydrolyze them, we're going to have aqueous acid, and we have to heat it up in order for this to work. Otherwise, the compound will not be hydrolyzed. So by heating it up, we can get the carboxylic acid, and we can get ammonium. We end up with ammonium because, again, we're in acidic conditions, and ammonia would be a pretty strong base. We can also perform this reaction in basic conditions. Again, this is going to require heat, and we would end up with the carboxylate and ammonia. Now, it's actually a really good thing that amides are so difficult to hydrolyze. if they were easy to hydrolyze, we would be in really big trouble because we are made up of largely amides. Take a look at any protein chemistry. Your amino acids are carboxylic acids and amines in one compound. And the way that they are connected is through a condensation reaction that forms a peptide linkage. A peptide linkage is just a fancy word that the biochemists use to describe an amide. So we are literally held together by amides. Now our last species are the nitriles. Nitriles are also fairly unreactive. So if we want to hydrolyze a nitrile, it's going to take aqueous acid, and heat is a must. And we can get a carboxylic acid, or we can do this in basic conditions in heat and get the carboxylate.